So in our last video we have seen about coordination compounds. So in coordination compounds we have seen the isomerisms, right? So in our last video we have seen about isomerisms. There are two main types of isomerism: stereo isomerism and structural isomerism. The stereo we have seen two: geometrical and optical. Structural isomerism, there are four types of isomerisms, which are the linkage isomerism, coordination isomerism, solvent isomerism. The isomerisms that we have seen in our last video. And today's video we will see the bonding in coordination compounds. There are two theories, VBT and CFT. VBT is valence bond theory and CFT is crystal field theory. In today's video we will see about the valence bond theory, what is valence bond theory and the limitations of valence bond theory. So let's start with the video. So coordination in bonding in coordination compounds. Now Werner was the first to describe the bonding features in coordination compounds. So Werner was the first scientist who described the bonding features in coordination compounds. But his theory could not answer basic questions like, now he being the first person to feature the bonding in coordination compound, but his theory was not able to explain certain questions or certain phenomena. Now what are the first one is why only certain element possesses the remarkable property of forming coordination compounds. So he was not able to explain why only certain elements possess the property of forming coordination compounds. Now why only transition metals form the most of the coordination compound? Why don't other molecules form? Why don't bases form? Alkali metals, why don't they form a coordination compound? Why only transition metal form the coordination compound? So these are certain things that Werner's theory was not able to explain. Second is why the bonds in coordination compound have directional properties. Okay, why they show a directional property. Third thing is why coordination compound have a characteristic magnetic and optical properties. Why they show magnetic and optical properties. So these are the things which Werner was not able to explain by his theory. Now, many approaches have been put forth to explain the nature of bonding in coordination compound. Okay, so since Werner was not able to explain these points, there were many scientists who put forth their way of explaining the bonding in coordination compounds. Among them are the valence bond theory, that is VBT, crystal field theory, that is CFT, ligand field theory, LFT, and molecular orbital theory, that is MOT. These are some of the theories which were put forth for explaining the bonding in coordination compounds. Now, we shall focus our attention on elementary treatment of the application of VBT and CFT of coordination compound. So for y'all, as of now, you only have the basics or basic treatment of valence bond theory and crystal field theory. Rest are there for you in higher classes. Okay. So first let's start with the valence bond theory. Now, according to this theory, the metal atom or ion under the influence of ligands can use n minus 1d ns np or np ns np nd orbitals for hybridization. Now what type of hybridizations are this? N minus 1 d ns np. What is this hybridization? This is dsp hybridization. Okay, and you have spd hybridization also, which is given in the next thing, that is ns np and nd. Right, this ns np and nd stands for spd hybridization, and n minus 1d ns and np, this stands for dsp hybridization. I think this hybridization and all you have learnt in your lower class, that is in your 11th standard. Okay, now to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar and so on. Now according to this theory, according to valence bond theory, the metal atom or ion, okay, the central metal atom or ion, it under the influence of ligands. Okay, basically central metal atom is always under the influence of ligands, right? There are ligands bound to the central metal atom. So this central metal atom or ion under the influence of the ligand, okay, can use any one of this hybridization. Okay, can undergo any one of this hybridization to yield a set of equivalent orbitals, to get a set of similar orbitals of definite geometry with a fixed geometrical shape. Now this is an octahedral shape. So like this, the hybridized orbitals yield an equivalent orbital with a definite geometry, such as the geometry can be octahedral, tetrahedral, square planar and so on. Now these hybridized orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for bonding. Now here they are explaining the bonding method, how the bond is formed. So when this metal atom ka orbitals are hybridized, okay, those hybridized orbitals, they allow the overlap between the ligands. Okay, now during 11th standard we have learned about the overlapping of the metal atoms. We had molecular orbital theory also, right? Now there we have learned the basic overlapping system. Now that overlapping thing is happening in the coordination compounds. The hybridized orbitals of metal atom, they overlap with ligands of the hybridized orbitals of the metal atom overlap with the orbitals of the ligand. Okay, because during this overlapping there is a sharing of electrons, or the ligand donate its electron to the metal atom to satisfy its valence electrons. Thus there is a bond formation occurs, okay, by the donation of electron pairs. Now this is illustrated by the following examples, and there are examples given. I'll explain them to you. First, let's see the coordination numbers, types of hybridization they give, and the geometry or distribution of hybrid orbitals in the space, how geometrically they are arranged. Now if the coordination number is 4, you can get an sp3 hybridization, or you can get an dsp2 hybridization. Now when there is sp3 hybridization, the structure is tetrahedral. When there is dsp2 hybridization, the structure is square planar. When there is 5 coordination number, the type of hybridization is sp3d hybridization, and the structure is trigonal bipyramidal. Now there are 2 types of hybridization with coordination number 6. One is sp3d2 or d2sp3. Okay, both form an octahedral structure. We'll see the examples. It is usually possible to predict the geometry of a complex form from the knowledge of its magnetic behavior on the basics of the valence bond theory. Now because of the valence bond theory, we can get to know about their magnetic behavior. Now, there are 2 types of magnetic behavior. Mainly there are 2 types, paramagnetic and magnetic. Now what is paramagnetic? When there is unpaired electrons in the valence shell, it is paramagnetic. And and where there is no unpaired electrons, it is diamagnetic. Okay. Now, in the diamagnetic octahedral complex CONH3 6 3+, the cobalt ion is in +3 oxidation state and has the electron configuration of 3d6. The hybridization scheme is as shown in the diagram. Now, how the hybridization takes place? Now, this CONH3 6 3+, this complex is diamagnetic. Okay. Being a diamagnetic molecule, how it became a diamagnetic molecule? Here, cobalt ion in its +3 oxidation state. Okay, 3d6 it gives. Okay, cobalt ion का +3 oxidation state, you get a 3d6. So 6 electrons in the 3d molecule. Now it gives you a D2sp3 hybridization because here 3d is involved. D orbital is first, no? Since D orbital is first, we will follow the dsp hybridization. Okay. Now in this case, what happens is we get a 3d 4s 4p. It is D2sp3 hybridization. Hybridized orbitals of cobalt. Now from here 1 electrons will transfer. Okay, so you get a D2sp3 hybridization. How? Now I will show you how it gets it. Now cobalt in its +3 state, okay, this is 3d 6 4s and 4p. Okay, 3d 6 electrons are there, no? 1 2 3 4 5 and 6. Now in hybridization, what happens is these electrons, where they are singly filled, they pair up. Okay, so this electron will go here, this electron will come here. So what it will become? It will become like this. 1 2. Since these 2 electrons are pairing up, it will be 3 4. Since these 2 electrons are pairing up, 5 6. The remaining orbitals as it is. Now from here till here, how many orbitals are empty? D 2 orbitals are empty. S 1 is there and P 3 is there. So it is a D2sp3 hybridization. So this is how we get a hybridized orbitals. Now these hybridized orbitals, they intake all the electron pairs donated by the ligand to form a bonding. Okay. Inner orbitals of the lower spin complex. Now here you get 6 pairs of electrons from the NH3 molecule. So into this empty orbitals, there are total how many pairs? 6 pairs of electrons are added. Now this 6 pairs of electron are donated by NH3 molecule. Okay. 6 pairs of electrons are donated by the NH3, which is the ligand. This is how the bonds between the coordination compound form. Now here bond is formed between cobalt and ammonia. Now the bond is formed by sharing of the or donating of the electron pairs to the central metal atom. 6 pairs of electrons, one from each NH3 molecule, occupy the 6 hybrid orbitals. Now these are the 6 hybridized orbitals, and each of the hybridized orbital occupies the electrons which are donated by the NH3 molecule, each of the NH3 molecule. That is why it is NH3 6. It is CO NH3 6. Why 6? Because there are 6 hybridized orbitals which requires the electrons from the NH3 molecule. So there are 6 NH3 molecules which are utilized. Now thus the complex has an octahedral geometry and is a diamagnetic because of the absence of unpaired electrons. Now here you can see all the electrons are paired. So since there is absence of unpaired electrons, it is diamagnetic. Then the formation of this complex, since the inner d orbital 3d is used in hybridization, the complex CONH363 plus is an inner orbital or a low spin or spin paired complex. Since here first molecule is the 3d orbitals, okay, there are inner 3d orbitals which are used because these two are the 3d orbitals. No, since there are inner 3d orbitals which are used or which are hybridized, the complex is known as inner orbital or low spin or spin paired complex. Now the paramagnetic octahedral complex, that is COF6. Now this is an example of diamagnetic octahedral. Now we have a paramagnetic octahedral complex, that is COF6. Okay, COF6 uses a outer orbital of 4d hybridization. Okay, now COF6, it uses an outer orbital, okay, of the 4d complex. Now it is thus called as outer orbital or high spin or spin free complex. Now here we have used the 3d orbitals for the pairing. See, that's why we first write it as D2sp3. This is an inner orbital, okay, or a low spin. In the second example, that is COF6, okay, here we will be using an outer orbital or the high spin or the spin free complex. Okay, here what happens is the hybridization will become sp3d3 hybridization. Now how it will become sp3d3 hybridization is, CO, that is cobalt, again it is in 3 plus oxidation. This is 3D, 4S, 4P and 4D. Now 3D is in 6 again. So 1, 2, 3, 4, 5 and 6. Okay, 6 electrons in 3D. Here along with cobalt, who is paired? Fluorine is paired. F6 is there. Fluorine, okay, is a strong ligand. Okay, since fluorine is a strong ligand, we cannot use the 3d orbitals. We have to go for an additional extra orbital. So here the hybridization won't occur with the inner orbitals, but it will occur with the outer orbitals. In case of first example, the hybridization occurred with inner orbitals because ammonia is a weak ligand or it's a neutral ligand, whereas fluorine is a strong ligand. So the hybridization will occur with an outer orbital. So the hybridized orbitals will be 4s, 4p. How many it is now? 4. How many f orbitals we have? 6. Fluorine 6, no, f6 it is. So 1, 2, 3, 4, 5 and 6. Okay, so here we can see the hybridization is sp3d2. Okay, orbitals from the 4d, two orbitals from the 4d, so it is sp3d2. Now we have seen two types of hybridization, d2sp3 and sp3d2. Both are octahedral. Okay, both are octahedral, but why there is d2sp3 and sp3d2 formation? Now this is formed when there is a weak ligand or a neutral ligand, whereas this is formed when there is a strong ligand. Okay, now here sp3d2 is formed, so the fluorine will donate its electrons in this format. Okay, now why it is paramagnetic? This D3d6, there is still 4 unpaired electrons which are there, that's why it is a paramagnetic molecule, or therefore it is paramagnetic in nature, because these 4 electrons will remain unpaired. In tetrahedral complexes, and these are the octahedral complexes that we have seen. In tetrahedral complexes, 1s and 3p orbitals are hybridized to form 4 equivalent orbitals oriented tetrahedrally. Now in a tetrahedral complex, we uses 1s and 3p orbitals which are hybridized, and it forms an equivalent orbitals which are oriented or which are arranged in a tetrahedral manner. Now this is illustrated in an example of NiCl4 2 minus. So NiCl4 2 minus, nickel tetrachlorine. Now here nickel is in +2 oxidation state and the ion has the electronic configuration of 3d8. Now why +2? It is 2 minus. On overall charge is 2 minus. So the nickel will be in a +2 form, because to satisfy or to attain a stability. Now the hybridization scheme is as shown in the diagram. Now since nickel is in +2 state, the 3d orbital will have 8 electrons. Okay. Nickel +2. So 3d will be 8 electrons. Now in this case, what will happen? 1, 2, 3, 4, 5, 6 and 7. Okay. Now we have to fill it with 8 electrons. 1, 2, 3, 4, 5, 6, 7 and 8. 8 electrons are filled. Now again, each Cl ions, here what will happen? The hybridization will be Cl is the one which will be donating its 4 electron pairs, right? So Cl is again a strong ligand. So the hybridization will be outer orbital hybridization, that is 4s and 4p. So it will be sp3 hybridization, and the electrons will be donated by the Cl molecules into this outer orbitals. Okay, so it is a sp3 hybridization. Now each Cl ions donate a pair of electrons. The compound is paramagnetic since it has 2 unpaired electrons. Now these 2 will be unpaired, right? So it is paramagnetic in nature. Similarly, NiCO4 has a tetrahedral geometry but is diamagnetic since nickel is in zero oxidation state and contains no unpaired electrons. Okay, NiCO4. Okay, this also has a tetrahedral geometry, but here CO4 is a weak ligand, so it is diamagnetic because this will be pairing up. Okay, and because of the zero oxidation state of the nickel will be in a zero oxidation state. These electrons will be paired up and contains no unpaired electrons. So since this will be paired up, the electrons will be directly moving to an sp3 hybridization. Now in the square planar structure, now we have seen octahedral, tetrahedral. Now the last one is the square planar structure. When there is a square planar complex, the hybridization involved is dsp3 hybridization. Now the example is NiCN4. Here nickel is in +2 oxidation state again and has an electronic configuration of 3d. Now the hybridization scheme is as shown in the diagram. Again, Cn is a weak electrolyte, weak ligand. So the inner d orbitals will be used. Now this electron from the d orbital, it will pair up with this unpaired electrons. So one unpaired orbital will be there, which will be mixed with the 4s and 3p ka 2 orbitals. So it will be dsp2 hybridization. Okay, one will be remaining like that only. And why one will remain? Because one of the d orbital is involved right here. NiCN4. So again, nickel we have 1 2 3 4 5 S and P 3 D8 1 2 3 4 5 6 7 8. Now this will pair up with this, so it will become 1 2 3 4 5 6 7 and 8. This orbital is remaining empty. This will pair up with the other two orbitals. So 3d ka 1, 4s 1 and 4p 2. Because how many Cn molecules will be sharing the electrons? 4 Cn molecules. So we only want 4 unhybridized orbitals. So 3d 1, 4s 1, 4p 2. 1 4p will remain unpaired, or 1 4p is not hybridized. So this is dsp2 hybridization for square planar structure. Now each of the hybridized orbitals receives a pair of electrons from the cyanide ion. Now, the compound is diamagnetic as evident from the absence of unpaired electrons. Since there is an absence of unpaired electrons, it is diamagnetic in nature. Now it is important to note that the hybridized orbital do not actually exist. In fact, hybridization is a mathematical manipulation of wave equation for the atomic orbitals involved. Now, in actual scenario, this hybrid orbitals, it does not actually exist. Okay, it is what we learn. Hybridization, it is a mathematical manipulation for a simplification to understand what exactly is happening. Okay, as of real, the hybrid orbitals doesn't exist. Now, the magnetic property of coordination compounds. The magnetic moment of coordination compound can be measured by the magnetic susceptibility experiments. The results can be used to obtain information about the number of unpaired electrons and hence structures adopted by metal complexes. Now, why magnetic property of a coordination compound is important? It is important because using the magnetic moment, we can measure the magnetic susceptibility. Okay, now the magnetic moment of a coordination compound, this magnetic moment, it can be measured by the magnetic susceptibility experiments. Now the results of this experiment can be used to obtain the information of number of unpaired electrons, because it will show the magnetic effect due to the unpaired electrons, right? So this magnetic moment experiment or magnetic susceptibility experiment will help you to know the number of unpaired electrons and hence the structures that are adopted by the metal complexes. Now, critical study of the magnetic data coordination compounds of metals of the first transition series reveals complications. Now, there are complications in the magnetic data of the coordination compound of first transition series. Now, for metal ions with up to 3 electrons in d orbitals like titanium, vanadium, chromium, 2 vacant d orbitals are available for octahedral hybridization with 4s and 4p orbitals. Now these elements, that is titanium, vanadium and chromium, they have a 2 vacant d orbitals. Now these 2 vacant d orbitals can form an octahedral structure with 4s and 4p, that is d2sp3 hybridization it can form. Now the magnetic behavior of these free ions and their coordination entity is similar. So here their magnetic behavior and the coordination entity is similar. When more than 3d electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available as the consequences of Hund's rule. So here these molecules will give you directly 2 vacant d orbitals, but in case there are the higher electrons or higher elements, they show more than 3d electrons, right? Now those elements require a pair of 3d orbitals for octahedral hybridization, which is not available. Now that is not available because of the Hund's rule. Thus for 3d4 Cr2 plus Mn3 plus, there are oxidations which are done for those molecules. A vacant pair of d orbital results only by pairing of 3d electrons, which leaves 2, 1 and 0 unpaired electrons respectively. So in that case, if you want a hybridization, we have to oxidize them to 2 plus 3 plus, which will result in vacant pair of d orbitals, results only by the pairing of 3d electrons. Here we have seen the pairing of 3d electrons, right? They are paired, leaving you 1 vacant d orbitals. In higher examples, we have seen pairing of 2 electron pairs and they are making vacant of 2 d orbitals are kept vacant. So which is the result of pairing of d orbital electrons, hence leaving 2, 1 and 0 unpaired electrons respectively. Now the magnetic data agree with maximum spin pairing in many cases, especially with coordination compounds containing d6 ions. So magnetic data, it agrees with a maximum of spin pairing. Now however, with species containing d4 and d5 ions, there are complications. d6 will give you directly a spin pairing, whereas d4 and d5 there are complications, has magnetic moment of 2 unpaired electrons, while MnCl6 3 minus has a paramagnetic moment of 4 unpaired electrons. Now these are the reasons for the magnetic spin or maximum spin pairing. Because of this spin pairing, we have something known as outer orbitals and inner orbitals, right? Inner orbitals, there are spin paired orbitals, and outer orbitals are spin free orbitals. They are spin free because there is no internal bond pairing that takes place, whereas in inner orbitals there is internal pairing which is taking place, and it gives you a diamagnetic nature. Inner orbitals are basically diamagnetic, whereas outer orbitals are paramagnetic in nature. So this is how the magnetic property is explained by valence bond theory. What are the limitations of valence bond theory? Now, since it explained the magnetic properties, the bonding, how the bonding between metal atom and ligand is there are still some limitations to valence bond theory. Now, while the valence bond theory to a larger extent explains the formation, structure and magnetic behavior of coordination compounds, as I told you, it explains to a major extent the formation of bond, their structures, magnetic behavior. It suffers from the following shortcomings. So there are still some things which it cannot explain. Now those are, it involves a number of assumptions. So there are some cases where you assume it to be like that. So there are lot of assumptions which are done in valence bond theory. It does not give a quantitative interpretation of magnetic data. Now, it will only explain you the qualitative thing, whether it is paramagnetic or diamagnetic, which is a quality. It doesn't give you a quantitative data, like the magnetic effect is so and so. Okay, it doesn't give you a quantity, it doesn't give you a value of a magnetic data interpretation. Third is, it does not explain the color exhibited by the coordination compounds. So each and every coordination compound has a color specific to it. So valence bond theory, it doesn't explain the color exhibited by the coordination compounds. It does not give a quantitative interpretation of the thermodynamic or kinetic stability of the coordination compounds. Again, here you cannot do any thermodynamic or kinetic stability of the coordination compound. It does not give any such values for a thermodynamic or a kinetic stability of the coordination compound. There is no quantitative interpretation of thermodynamic and kinetic stability of coordination compound. It does not make exact predictions regarding the tetrahedral and square planar structures of 4 coordinate complexes. So it cannot make an exact prediction that this will form a tetrahedral structure or this will form a square planar structure. There are all assumptions that this might form a tetrahedral, this might form a square planar structure. So there is no exact prediction with the tetrahedral and square planar structures of 4 coordinate complexes. Last is, it does not distinguish between weak and strong ligands. Now, initially I told you all there is weak and strong ligands, but that is just to explain. Okay, valence bond theory exactly doesn't give anything with weak and strong ligands. Now, why there is inner orbital formation or why there is outer orbital formation, why the 3D orbital is involved, why there is a 4D orbital which is involving, those are because of the weak and strong ligands. Okay, but this concept was not explained by the valence bond theory. Okay, so this is what exactly the valence bond theory, the limitations of valence bond theory, magnetic property of coordination compounds, and what exactly the valence bond theory is. So thank you for watching my video. Please do like, share and subscribe to our channel.